Right, so let me record it and then get the sound. All right, now we're ready to go.
This is the Earth at a time when the dinosaurs roamed a lush and fertile planet. A piece of rock just 6 miles wide changed all that. It hit with the force of 10,000 nuclear weapons. 1 trillion tons of dirt and rock hurtled into the atmosphere, creating a suffocating blanket of dust the sun was powerless to penetrate for 1,000 years. It happened before. It will happen again. It's just a question of when.
Love this scene from the opening scene of Armageddon. All right, so here's the question. Asteroid impact. You got the fireball, creating a shock wave, so the shock wave is going to travel roughly about 1,000 miles per hour, causing all this destruction. So you got the fire, you got the heat, you got the shock wave, the sound wave. So what is the initial form of energy that the asteroid has creates all this havoc? So that becomes the main premise of the lecture. So far, we talked about conservation of mechanical energy. Okay, so this is a very limited application of the conservation of energy. All right, so what's being conserved in this case is the mechanical energy. So mechanical energy is the one that remains constant. That's what it means. All right, in terms of applications, the mechanical energy will become constant only if the work done by a conservative force like gravity. So what happens when you do work against gravity by lifting something up? So it's being lifted up against gravity. Work is being done on him. So which means that the energy gets transferred to him. So the amount of energy gets transferred to him becomes his mechanical energy, becomes his potential energy. So once you let go, it's got potential energy. So what happens? Gravity takes over. When gravity takes over, gravity is going to take that potential energy, and then it's going to convert it back into kinetic. So just before impact, the thing got going for him is he's got kinetic energy at this point. He's got kinetic energy. So the question is, perhaps that kinetic energy upon impact, where did energy go? So that's what we will discuss. Again, I end up discovering the concept of inertia. When I was trying to figure out the acceleration due to gravity, he was trying to measure it actually by slowing the motion down. And that he made the observation that if you ignore the effects of surface friction, this ball is going to go back up the same height. So the question became why. We know the reason why, because ignoring surface friction, only force acting is gravity. When gravity is the only force acting in a system, what happens? It's a conservative force. It takes potential energy, converts it into kinetic, and kinetic energy gets converted back into potential energy. That's it. Mechanical energy is going to remain constant because gravity is a conservative force. All right, so conservative force is what conserves mechanical energy. So what happens is, because mechanical energy is constant, kinetic energy, potential energy turns into kinetic energy turns back into potential energy. That's the limited case of conservation of energy.
His favorite part of the job is testing the products. He doesn't pedal. He uses his upper body to pump himself up to 35 miles per hour.
He doesn't pedal, but he swings his body back and forth. Right, so he's by using his muscles, he's generating a propulsive force. By
speed he needs to get
utilizing a propulsive force, he's gaining mechanical energy. He's gaining mechanical energy in a sense that starting off at the same point as this one does, or exact same height in essence, except now he gains mechanical energy. Right, so which means that his final mechanical energy is going to be larger than his initial mechanical energy. So the question is, where did that extra energy come from if that's the case? If you're getting mechanical energy using propulsive force, mostly what's happening is the chemical energy is the one that gets converted to the extra mechanical energy. Chemical energy is what you get from your muscles, what you have in your gas tank, your car. It's the chemical energy. All right. Chemical energy is something that we end up, living things usually get it through eating food. So obviously you can eat other animals as well as plant life. Plant life is going to end up getting their energy from light from the sun. We also get heat from the sun. Heat and light is what drives the chemical processes that keep life active here on Earth. So what happens within the sun is obviously you got a nuclear process that generates the light and heat. So what's happening is you got hydrogen using the helium inside the sun. So that's what sustains life here on Earth. So one of these forms of energy, in essence, is going to get converted into the actual mechanical energy that you're looking at. So there's going to be mechanical energy is going to be gained. Energy is not being created; it just gets converted from some other form of energy into the mechanical energy. All right, so there's a conversion that's happening. So even if there's a gain of mechanical energy, it's not that mechanical energy is getting created out of nowhere. It's just getting transferred from something else or somewhere else, in essence. All right, so when there's a propulsive force acting, what do we know? Mechanical energy is no longer conserved. It's not conserved in a sense that it's not constant anymore. That's what it means. So propulsive force does not conserve mechanical energy. When friction is present, the ball doesn't go back up to the same height. That's the reason why Galileo said, in the absence of friction, it should go back up to the same height, which means that he knew the ball wasn't going to go back up to the same height. All right, so which means that the final mechanical energy is not going to be the same as the initial one. Mechanical energy is going to be lost. All right, so when the mechanical energy is lost, immediately when you do a demonstration like that, you'll notice that there's going to be sound which is going to be generated. So sound is a form of energy. So mechanical energy is going to get converted into sound. If you measure the surface temperature is going to go up, which means that it's also going to get converted into heat. If there's too much friction, what happens is surfaces may heat up to an extent that surfaces will start to glow, which means that it can turn into fire. All right, once again, the lost energy doesn't mean that energy is destroyed. The mechanical energy is lost. It just gets converted into something else. So this brings us to the conservation of total energy. So when there's a propulsion system present, mechanical energy is no longer conserved. Mechanical energy is going to be gained. When friction is present, once again, the mechanical energy is not conserved because the mechanical energy is lost. All right, so when you gain mechanical energy, it gets converted from some other types of energy. When you lose mechanical energy, it gets converted to some other types of energy. So the total energy, in essence, remains constant. Non-conservative forces are important because now you can do a little bit more realistic computations. Right, so problem number 12, this sort of problem that we did before. Right, so it's an accident scene investigation. Okay, so this is one of the problems that I want you to focus on. Okay, so you guys have you've got the mathematical background to be able to solve something like this. All right, so accident scene investigation. So there's an accident on a rainy day. All right, evidently the driver locks up the brakes, the car goes into your skid, so you got the skid marks. So they measured skid marks as 233 feet. So the question is, how fast was the car moving at the time the driver locked up the brakes? So X is going to represent the length of the skid mark. So the vehicle is just going to slow down in this direction. And the only force acting on it is the kinetic frictional force, under the influence of the kinetic frictional force. So what is the speed at the time the brakes were locked up? So here's the measured distance. And it's a rainy day, so here's the coefficient of kinetic friction. What's the initial speed in terms of meters per second, miles per hour? All right, so we're done with the conversion. All right, so from the formula sheet, formula that we will utilize is this one. All right, so the work is a process of transferring energy. All right, so by the amount of work that you do, you will transfer this amount of energy. Work is a process of transferring energy. Energy is going to be transferred in the form of kinetic energy. That's what it means. Okay, it kind of makes sense because number one, this thing is moving. If the force is in the same direction, it's going to start to go faster, right? So which means that kinetic energy is going to increase. In this case, the force is opposing motion. So which means that it's going to reduce this kinetic energy. Force is opposing motion, so it's going to do a negative work, meaning that the kinetic energy is going to diminish. So if force is in the same direction, kinetic energy is going to increase. If the force is opposing motion, the kinetic energy is going to decrease. So it's important that you visualize it. On top of that, it's important that you know how to interpret these formulas. Once again, these formulas are summary statements. So the amount of work that you do is the same as the amount of energy that you transfer. Work is a process of transferring energy. In essence, you transfer energy in the form of kinetic energy. Because you either add to the motion of an object or you subtract from the motion of an object. That's what it means. In this case, force is opposing motion, so which means that it's going to diminish its kinetic energy. All right, so that's how you start it. Right, so kinetic energy, you got the expression for it, so it's going to be 1/2 mv squared. So work is a process of transferring energy, so which means that energy is going to be transferred in or out of a system in the form of kinetic energy. Kinetic energy is the same as 1/2 mv squared, so it's final speed. This is your initial speed, square of the final, and this is square of the initial speed. You know, the final speed is going to be 0, so this term goes to 0. Isolate the initial speed. Get rid of the mass from the left-hand side, and then multiply both sides by 2, and then get rid of this negative by multiplying both sides by the negative. Okay. All right, so next step is get rid of the square by taking the square root of both sides. All right, so we don't have an expression for W, so we don't know what work is. We don't have a number for it, but we got a definition for it. So by definition, the work is force causing displacement. And the angle is going to be important, but angle is going to be 0 in this case, right? So cosine of 0 is going to be 1. So it's getting force times displacement. All right, so the work is a combination of force and displacement. Okay, in this case, displacement is in the forward direction. Force is in the opposite direction. It's opposing motion. All right, so it's a combination of force and displacement. So by definition, that's what your work in. Work is, so here's the force, here's the displacement. That's it. So we'll do a back substitution. All right, so you got a negative, you got a negative, so it's going to give you a positive. And now we don't have an expression for the kinetic frictional force. We don't have a number for it, so it's not given. So, but we have a number for coefficient of kinetic friction. All right, so write out the formula for the kinetic frictional force. And we don't have an expression for N, so we will have to come up with an expression for it. You know, N is a normal force. It's a reaction force, it's a surface force. Surface force is a reaction force, in this case, to the weight of this vehicle. I notice that forces along the y direction. So we'll just sum up forces along the y direction. And is up, W is down. All right, and net force along the y direction is responsible for the acceleration along the y direction. Except this vehicle is not going up and down, so which means that there's no acceleration along the y direction. So that term is 0. So which means that normal force is the same as the weight, which is the same as mg. So which means that n becomes the apparent weight. So do a back substitution there. It gives you this expression. Again, a back substitution there. And then we're done. Okay, so mass is not going to matter. It doesn't matter that you're driving a Ford Tempo, a truck, it's SUV, or motorcycle. But the only thing that matters in terms of the distance that you will skid is the quality of the tires that you have. All right. So higher the speed is, the longer this thing is going to skid. All right. So larger the skid marks is, the bigger the speed is, in essence. All right. So it works out. So you do you plug the numbers in. All right, you get a number in terms of meters per second. So it's going to be 55 miles per hour. We've done the same calculation while we were studying the net force. So this is the second method. This is the conservation of total energy. All right. So this is something that you need to practice. This is a good practice problem. All right, this would be a fun little problem to solve. Yes. Anyway, so even if the mechanical energy is not conserved, total energy still is. All right, so which means that the energy cannot be created or destroyed. It can only be converted from one form to another. This got some interesting implications, which means that whatever the universe energy was available in the beginning of the creation of this universe or formation of this universe, forget the creation. I'm talking about Big Bang. The energy content of the universe is constant. All right, so the amount of energy available in the universe is exactly the same amount of energy there was in the beginning of the universe. That's what it means. So which means that the total energy in the universe is going to remain constant, provided that this is the only universe. It's kind of weird. If there are parallel universes, of course, if the energy is missing from this universe, it means that it must be leaking to a different universe, or it may be leaking into this universe. So the total energy content of the energy is still going to be constant all throughout the universes in essence. So that's what it means. So energy cannot be created or destroyed. It can only be converted from one form to another. Conservation of energy. Right, the best illustration of it, okay, so this. Before you turn on the ignition, obviously the only form of energy that the car has is the chemical energy, right? So it's the chemical potential energy. You turn on the ignition, engine is going to heat up because of friction. So chemical potential energy is converted into heat. Engine is going to roar, so it's going to turn into sound. And as soon as the car starts to move, part of that potential energy, chemical potential energy, is going to start to get converted into kinetic energy of the motion. And then, boom, the accident starts. Now you got a lot of friction, so it's dissipating motion. Here, tremendous amount of sound. It's a form of energy. Through friction, obviously, there's a tremendous amount of heat generated, so that's also a form of energy. And then, obviously, everything starts to glow, so you get fire, so that's a form of energy. On top of that, the vehicle is going to start to break apart. All right, so deformation is also a form of energy. There's two ways you can deform this. Number one, you can crush something. That's one way. You can dent something, crush something, or whatever. That's one way you could do it. You crush something, though, the energy remains within the vehicle itself. The second way of doing it is you can just break it apart. Yeah. At low speeds, it makes sense to make the cars crushable. Commercial cars are not meant to go really fast. Okay. Most accidents usually happen around 40 to 50 miles per hour, reasonable speeds. It makes sense to contain the energy within the vehicle. All right, you can make it crushable to increase the impact on, so that makes it survivable for the most part, provided that people inside are wearing their seatbelts. Okay, by design, that's the way it should work out. With these guys, it's different. For example, this guy was going about 150 miles per hour at the time this sort of accident happened. Okay. You don't want to contain that amount of force. amount of energy inside the car, because the energy is associated with the force that can do harm. Right. So more energy you contain within the vehicle means more force is available to harm the driver. You don't want to do that. There's no way you can generate a large enough impact time at those speeds by having the car crumple, because these cars will not have that kind of crumple zones, guys. It's out of the question. So the best thing to do is make the car fragile. So upon impact, you want parts to scatter all over the place, because with the scattering parts, the kinetic energy is taken away from the driver. Right. With these cars, the parts just flying off, those parts usually take the energy with them. So that's what you want. Right. So in essence, you try to diminish the amount of energy that can harm the driver. It means that you're diminishing the amount of force that's capable of harming the driver, in essence. All right, so these cars by design are designed to break apart. If you look at this, you'll notice immediately that you don't have any dents on this vehicle. It's by design. Obviously, it's completely sheared off.
Have you ever wondered, why is the sky blue? And why do flesh-eating meteorites rip through our universe? This ad exposes the God's honest truth.
All right, so you got all this fire and destruction or whatever. You got a fireball. You got the destruction. What's the initial form of energy that gets converted into heat, fire? All right. You guys have an answer for that, and your answer is usually not 100% accurate. All right, you guys have a commonsensical answer. You got this asteroid which is coming in, a collision trajectory with the Earth. All right, so this is like the premise of the movie Armageddon. Likewise, it's exactly the same premise for deep impact. Right, in deep impact, there's actually an impact that creates all this havoc. So the asteroid is coming in. So it's imagine it's coming in at 25 to 30,000 miles per hour. So it's got speed, right? So you guys are immediately thinking, oh, the initial form of energy that turns into heat, light, fire, which is the fireball that you have, the sound, and then eventually that causes the impact crater or deformation that you're looking at. I mean, through friction, you end up getting the heat, light, sound, and then obviously the crater, impact crater. You guys are thinking that the initial form of this energy is kinetic energy because this thing is coming at us at a fairly fast speed, like 25 to 30,000 miles per hour. You're thinking that the initial form of energy is kinetic energy. Okay, so that's actually partially correct. Notice that this is also moving under the influence of gravity, right? So what happens is it starts to approach the Earth's gravitational field is going to get stronger. It's going to get stronger, which means that this thing is going to start to accelerate towards the Earth. So which means that the gravity is going to feed energy to it, in essence. So this thing is going to start to accelerate, which means that this thing has also potential energy related to its position inside the gravitational force field. So the initial form of energy is not only kinetic, it also got potential energy coming in from space. So there's no friction to speak of, and gravity is a conservative force. So which means that the initial form of energy is going to be all mechanical. So it's moving, so which means that it's got kinetic energy. It's also moving under the influence of gravity, which means that it's also got potential energy. So it starts to get closer and closer to the Earth. The potential energy starts to turn into kinetic energy, which means that this thing is going to keep speeding up. So which means that the gravity is going to keep feeding energy to it. All right, so the initial form of energy, just before it hits the atmosphere, is going to be mechanical energy.
The principles of a trampoline are very basic. Up, down, up, through. The principles of a trampoline are very basic. Up, down, up.
So once again, there's a lot of physics here. I kind of rushed through it. It's not something I should be rushing through because this stuff is actually important. All right, so it's got potential energy, gravitational potential energy. That turns into kinetic energy just before, at the moment it hits the mat. And then as soon as it hits the mat, what happens? The mat is going to stretch. So which means that the energy gets transferred to the mat because there's a force acting on the mat. The mat stretches or it gets displaced in the direction of the force. So which means that there's work being done on the mat, which means that energy is being transferred to the mat. So which means that the combination of the mat and the person now has got potential energy. Now the mat's got something called the restoring force. It stretches and then the force is going to act in the opposite direction of the stretch to try to restore the mat back to its original shape. So which means that the amount of work that you do in stretching the mat is going to become stored in the mat as this potential energy. All right. So that potential energy between the mat and the person system, whatever that means, it's going to get transferred back to the person. It's going to turn into the kinetic energy of the person. and then the person is pushed up against gravity. So now it's going to turn into gravitational potential energy of that person. On the way back, it turns to kinetic energy, and then on the way back, it turns into the elastic potential or deformation potential energy of the matter as well as the person. It turns back into kinetic energy, turns back into gravitational potential energy, kinetic energy, and then the elastic potential energy of the mass. Notice what's happening. The energy gets transferred back and forth, back and forth. Okay. The reason why the energy gets transferred back and forth is because any work done against the conservative force, like gravity, becomes the energy stored in that mass. And any work done against the restoring force, any work done against the conservative force, like the restoring force, is also going to become stored in the mass in the person system that you're looking at. All right. Which means that the restoring force is also conservative force. Remember, guys, conservative force is what conserves mechanical energy. So, which means that if there's a conservative force acting in a system, the mechanical energy remains constant. So, gravity is a conservative force, something that we discussed before. Also, restoring force. Restoring force is a conservative force. All right. So, I kind of discussed that real fast. We needed to also express things in the form of mathematics. So, we're going to be talking about the restoring force. Restoring force within the context of elastic potential energy. We talked about the gravitational potential energy. Now we're talking about elastic potential energy. Okay, so elastic potential energy is the amount of energy that you transfer to a system when you deform the system. You apply a force on it, the system is going to deform, and there's going to be a restoring force that's going to try to restore the system back to its original position. All right, example of it is a spring mass system. All right, so you got the spring, you got the mass, and here's the original position of the mass. I can draw this correctly. So what I'm doing is I'm actually compressing this mass in this direction. So you got the spring system, and then you just push the mass in this direction, in this x direction. Okay, negative x direction. So this is the uncompressed position of the mass. And then when you, or this mass spring system, and then you just push it in this direction. When you compress it in this direction, what happens, there's going to be a restoring force. It's going to act in the opposite direction of it. The restoring force is going to try to restore the system back to its original position. So the amount of restoring force that the system has, the amount of restoring force which is going to become, which is generated. Okay, I'm just having a really hard time finding the right vocabulary. Okay, so the amount of restoring force that becomes created is probably a better term. Depends on the amount of compression. So more you compress this, the bigger the restoring force is going to become. Also, it depends on K. That's just a constant. This is K tells you how stiff this spring is. So given the stiffness of the spring, more you compress it, the larger the restoring force is going to be. All right. So F, obviously, in this case, is your restoring force. X is either the compression, you can compress it. When you compress it, the restoring force is going to be in the opposite direction. That's the reason why we get a negative, which means that the restoring force is always going to be in the opposite direction, or either the compression or stretching, elongation, or the stretching of it. So you can either compress it or you stretch it. If I stretch it this way, restoring force is going to act in the opposite direction, trying to restore the system back to its original position. All right, and K is going to tell you how stiff the spring is. It's known as the spring constant. It simply tells you about the stiffness of this spring. Okay, so this thing that we're talking about is known as the Hooke's law. All right, something about Hooke's, it's just the background stuff. He was a contemporary of Newton, and absolutely Newton and Hooke absolutely hated each other. It's weird. Now, Newton was probably about 20 years younger than Hooke, and I think Hooke was extremely jealous of Newton, and he was very critical of Newton. And Newton, I don't know what kind of personality. I think the guy was definitely on the spectrum. He was not very sociable, obviously. And he was really offended. Newton did not want to deal with people, and especially he didn't want to deal with Hooke. So at that point, he completely stopped publishing any of his work. The laws of motion, law of gravity, and the fact that he invented calculus. He sat on that information for 20 years until Hooke passed away. All right, he would talk to his friends from time to time. People who knew him personally knew that he had this wealth of knowledge, but he was not willing to share it, and he was not willing to publish any of his work. So, Hooke's law gives you the restoring force, and restoring force, just like gravity is, it's a conservative force. So, which means that whenever you do work against something that stretches or whatever, there's going to be or compresses. You can store energy in that object. All right, so by compressing it or stretching it, whenever you do work against a restoring force, which means that you're able to transfer energy into that system. In this case, it's a mass spring system or spring mass system. Okay, so the amount of energy that you store in it is going to become obviously part of the energy of that system. It becomes stored in that system. So which means that the system is going to have potential energy. Potential energy depends. I say P, so that's potential energy. Depending upon the book that you're using, you may use P, you may use the letter U, or sometimes they use the letter V. Either way, it's the same thing. So the amount of energy that's becomes stored in the system is going to be given by this equation. All right, so the restoring force is a conservative force. So what that means is the mechanical energy is going to be conserved. Mechanical energy is a combination of kinetic and potential energies. There's your kinetic energy, there's your potential energy, which means that it's going to remain constant, which means that it's going to be conserved because of the simple reason that this force, the restoring force, is a conservative force. It's like gravity is. So work done against gravity goes into the potential energy of the object that you're lifting. And the work done against the restoring force is just going to go into the potential energy of the system. Right, so you deform something by stretching it or compressing it. So that's the amount of work done against the restoring force. So that's what happens to the mat. Every time this person was coming down, he was stretching the mat, so he was storing energy within that system in the form of its potential energy. Simple application of this is problem number 10. All right, so what do we have? We have a dart gun. You got the dart gun. So you have a spring, compressible spring. This is the uncompressed position, and this is the compressed position, obviously. Right, so this is the uncompressed, so which means that the compression is 0, so it's got 0 compression here. And then you compress it in this direction, so which means that the spring is compressed. This looks like a, so this is your dart. So initial compression is going to be 6 centimeters. As soon as you fire the gun, it goes back to its original position. So the final position, final compression is going to be 0. So that's the uncompressed position. So that's the mass of the dart that we're looking at. Stiffness of the spring is your spring constant. Initial speed is 0. So the question is, what's the speed of the dart when you fire it, when it's projected? In terms of meters per second to miles per hour. That's 10 meters to meters conversion. Straightforward. Okay. We're ignoring the surface friction, obviously. So if that's the case, mechanical energy is constant. Final and initial mechanical energies are the same. All right, so mechanical energy is a combination of kinetic and potential energies. Kinetic energy is right here. Potential energy of this spring mass system is going to be located right here. So the potential energy of the spring is going to be right there. Okay, so it's going to be 1/2 kx squared. So this is the final kinetic, final potential, initial kinetic, initial potential energy. All right, so next step is if we have any zeros, let's plug in the let's plug in the zeros. All right, so what do we have? So initial speed is 0, so this is going to go to 0. And if final compression is 0, so it's going to be an uncompressed position, so that's going to be 0. So this expression goes to 0, so it's this one. Now we got the simplified algebra, so you have 1/2 on both sides, multiply both sides by 2, and then divide both sides by m. So you got your cancellations all over the place. Okay, right, and then stop at this point. Okay, it's the final equation. Okay, so once we get on the math track or algebra track, at that point you follow the rules of algebra, then you come up with an expression. In physics, what thing that we do more than anything else is these are summary statements. There's a conclusion here. So the speed of the dart is going to definitely depend on the amount of compression that the spring is going to experience. So the more you compress it, the faster the dart is going to move. Okay, so that's one conclusion. You can draw 3 conclusions out of this. This is beautiful. The stiffer the spring is, the faster the dart is going to move. Also, the third statement that comes out of it is the more massive the dart is, the slower it's going to move. Okay, so you end up getting 3 predictions out of it. So the more you compress the spring, faster it's going to move. Stiffer the spring is, the faster it's going to move. And more massive the dart is, the slower it's going to move. Anyways, you plug the numbers in, you get something which is about 7 miles per hour. In reality, with the surface friction, is probably getting close to 6. So it's a good estimate. Yeah, so it's a cute way of doing these problems.
June 20th, 19.
Guys, take a break for 10. Only the sprinters can run that fast. Case in point.
A human being go without machine power.
2 seconds into the race. I can't even
When he broke the world record in
think about that
1956.
at that point.
He's going a little bit over 23 miles per hour.
After 4 years of intense training, breaking the tape in first place brings a mixture of emotions.
Yeah, it's a lot of different things. It's, it's relieved that the race is over, relieved that you didn't screw up, and you're happy that you were successful. And it's definitely.
All right, so there's no way
A
you're
human
running that fast with a 4 in your hand. If you could run at 21.5 miles per hour, with a pull, she could be sprinting around 25 to 26. So that's not reasonable. All right, so which means that a couple of assumptions that we made were not correct. Number one assumption, which is a horrible assumption, you can't take initial height to be the ground, okay? Because you should be keeping track of the center of mass. All right, so the person is trying to get the center of mass above this hurdle. So center of mass is located high up. People tend to be fairly tall, so her center of mass is going to be just about where her belly is. So it's about 3 feet, maybe about 4 feet above the ground. About 3 feet, that's reasonable. All right, so there's no way she's running at 21 to 22 miles per hour. Reasonable speed for her is about 14 to 15 miles per hour. Even 14 to 15 miles per hour is way too fast, but it's doable. And some of these guys could go up to about 18 to 19 miles per hour. But she's been at beach world championships, so I don't think she's that fast. 15, possibly 16 miles per hour is what I'm looking at. Even with that assumption in mind, if she's going about 14 to 15 miles per hour, if all that kinetic energy goes into bending the pole is not going to have enough energy in it that's going to actually going to elevate her to this height. So all that potential energy stored inside the pole, is going to turn into her potential energy. The pole is not going to have enough energy stored in it to actually propel her over the bar. It's not going to happen. All right. The question is, where does she get extra energy from? All right. So the question is, where does she get extra energy from? What's happening is, notice that if you just follow him in this case, just follow the center of mass. So center of mass is located right here. So center of mass is here. Center of mass is here. Notice that by the time the pole stretches, the center of mass is getting right here, and there's a distance. There's almost 1 foot to 2 feet distance. All right. So by the time the pole actually stretches back to its normal position, all right, the center of mass is still going to fall short. So the rest of the energy is going to come from the muscles, in essence. So it's the chemical potential energy. All right. It depends on how strong you are, how powerful you are. All right, how coordinated you are at that point. And you guys knew that she was strong enough to actually just to close the gap right there at that point. So the extra energy comes from muscles, and the muscles usually utilize the chemical potential energy. So that turns into heat and whatnot. And then the person gets over the hurdle.
The referee says take
All right, so next topic of discussion is power.
the strain, and what a strain it's going to be. Those starting blocks again hammered into the ground. That gives the competitors a firm grip. It's almost like a rowing action, and good rhythm is going to be so important. Look at that effort in his face. His legs will be burning. His arms are surely hurting now. The clock will stop any moment now, 42.36, and that is a strong target. He nods, he's ready, and now the effort. Every time this man steps up to take part in an event, the crowd go absolutely wild. And this clapping won't do him any harm at all. It's setting up a rhythm, and that's what he needs to go for a good time. Coming up to 30 seconds, it certainly is going to be very fast. 34.34, that has to be the winning performance. The clock will stop any moment now, 42.36.
All right, so if I were to ask you which guy is more powerful,
That is a strong lead, the winning
you got the answer, right? All right, so it's the same airplane, the same distance.
performance.
The amount of work that both of them are doing is, force times displacement. It's a combination of force and
The clock will
displacement.
stop any moment now,
Except one guy does it in a shorter amount of time.
42.36.
So if I were to ask you which guy is stronger,
And that is a strong target. 34.4.
the first guy takes 45 seconds. The second guy is going to take about 35 seconds.
That has to be the
All right, so the second guy was able to do the same amount of work faster, so which means that he's going to be more powerful.
winning performance.
All right, so power means a couple of things, all right, in terms of physics. All right, number one, power is how fast the work is done. All right, so work is a process of transferring energy, so which means that how fast the energy is transferred. All right, and when you transfer energy, obviously you could also be converting energy, so how fast the energy is converted. All right, so that's what it means. How fast the work is done, how fast the energy is transferred, and how fast the energy is converted. All right, so mathematically, how fast the work is done is the rate at which the work is done, so it's work over time, how fast the work is done. Okay, work is the process of transferring energy, so it's the amount of energy that you transfer. So W becomes delta E, so how fast the energy is transferred, so that becomes the second statement. And then we end up getting something interesting out of this. But also, work is a combination of force, cause, and displacement. So there's force and there's displacement, right? So when you do a back substitution into this expression, notice that there's displacement over time. A little expression means speed. Okay, so which means that how fast force is transferred, in essence. That's kind of weird. All right, so the last statement is a combination of force and the speed of that force. All right, so how fast the force is transferred is also going to be your power. All right, so from the formula sheet, we got a bunch of expressions. So power is how fast the work is done. how fast the energy is transferred, so the transferred energy can appear in form of kinetic energy. Or if the power is how fast the work is done by gravity, so gravity diminishes the potential energy. And power also means how fast the force is transferred. Okay, guys, you see these W's or omegas, it's not intentional. All right, so when I was transferring stuff and changing format for whatever the reason, the word ended up putting those W's in. I just didn't know how to delete them. So just ignore that. They're in the formula sheet unintentionally. Okay, so P here means power. It's going to be expressed in terms of W. W is going to be watts. All right, so here, that's the reason why I use brackets. So here, W is not the same as work. So this is your work. So it's going to be in terms of joules. T is going to be time. So work is in terms of joules. So it's going to be joules per second, which is otherwise known as watts. All right, so this W means watts. In the United States, we use horsepower. So 1 horsepower is going to be 746 watts. Okay, so that's everything you need to know about power. So power is how fast the work is done, how fast the energy is transferred, how fast the energy is converted. Proper unit is watts. We use horsepower in the United States. All right, speaking of horsepower, obviously the common way of expressing power in the United States is horsepower when it comes to cars. Right? Expensive cars, the cars can have really amazing accelerations, like 0 to 60 or whatever. You're looking at anything over 200 horsepower usually. Right? My Ford Tempo, its horsepower was about 120, but it didn't drive like all the horses were pulling in the same direction though. All right. So you can figure out the horsepower of your car. It's fairly easy. Okay, so a couple of things you need to know about your car. Number one, look up its weight in terms of pounds. And then try your best check to see how long it takes to measure the time. Okay, I think we can make this a lab project for next week. Okay, so you will go from 0 to 60 and just time it. Okay, it should give you the average power of your car, the engine, and then you can compare it to the listed power. Okay, so just look it up on the internet. It's kind of neat. So the car is going to go from 0 to 60 miles per hour within this time period, so which means that the car is going to accelerate in the forward direction. Here's the mass of the car. All right, and initial speed is going to be 0. It goes from 0 to 60 within 7.4 seconds. Okay, so it's like a regular family car, so that's not bad. So what's the power of the engine in terms of watts and the horsepower? All right, so do the conversions to the metric unit. All right, so the next thing we need to do is we need to figure out the right formula. So the power is going to be located here. So here's the formula for power. And obviously, it's how fast energy gets converted into kinetic energy of the car. So that's what we're going to be looking at. So write out the formula. So it's how fast the work is done, how fast the energy gets converted into kinetic energy of the car. So kinetic energy by definition is going to be 1/2 mv squared. So right here, so it becomes this. All right, so the speed goes from the initial speed to the final speed. We know that the initial speed is 0, so that term goes to 0. All right, so that's it. All right, so do a back substitution. And then just clean it up. All right, that's the final expression. And then plug the numbers in. Get an expression in terms of watts converted to horsepower. And it says the car's horsepower is 90 horsepower. All right, it's reasonable. Okay, that's how you can figure out the horsepower of your engine. And this is something that you will do maybe next week or a week after, because I got a bunch of take-home labs for it. Okay, this week's take-home lab is going to be free-file experiment that you will do. Okay. Okay, this is a bit of a challenge problem. All right, so notice that this car is climbing up a 10-degree hill in essence. And it's doing so at a steady speed, so constant speed of 60 miles per hour. So there's a returning force acting, so that's the frictional force, the surface force. So the question is, what's the power required for the car to climb up this hill at a constant speed? All right, so how would you do a problem like this? All right, so I will just redraw this. I'm just going to get the center of mass. Right, so the hill is set to 10 degrees with respect to the horizontal. It's got mass, so this is a 3,000-pound car, just like the previous one. It's got weight in the downward direction, so it's sitting on a surface. So I'm doing my force diagram. It's got the normal force going in there. It's going to be 90 degrees to the surface. Retarding force is the frictional force opposing motion. And it's moving at a steady speed in this direction, so which means that there's going to be a drive force in this direction. Thrust, the drive force, propulsive force, propulsion. Okay, I'll use D for the drive force. All right, because I get a force diagram, what I need to do is I need to express my forces on a coordinate system. So I'll have my x-axis parallel to the surface. All right, so the y-axis is going to be 90 degrees to it. All right, so that I can do my force summations accordingly. All right, so this angle is the same as that angle. All right, so this is what I'm pointing out here this little thing that I did, reason why you guys did so badly, and just about, with the exception of one or two of you guys, most of you guys usually struggle with mathematics. Okay, so which means that you need to spend a little bit more time practicing it. You cannot solve these problems unless your force diagram is set up correctly. So which means that you guys are either memorizing it or obviously you're looking it up. You don't have a choice. You're looking it up. And almost like, because it's almost like a take-home test, you're thinking, oh, I can just fake it, because if it were an in-class test, I would not let you use your notes. Okay. If you don't practice it, it's not something that you can come up with within the last minute. Okay, your force diagrams are not set up right to justify your solutions. If you don't set it up and you are just solving it as if it's a math problem, it shows. You guys there are 1,000 assumptions that go into solving these problems, and your assumptions are not clarified. You're just dropping equations all over the place, and you are assuming that this is an algebra problem, which it's not. So it's glaringly obvious that you have no idea what you're doing. All right. As a result, I'm forcing you to take those tests, which means that you have to do an upgrade on it, because your work does not justify. The way you set it up, it does not justify a solution. Notice that every time I'm setting something up, everything is clarified. All right, this is called showing work. When you do a test problem, you show work in a sense that it's almost like explaining what you're thinking to someone who doesn't know what you're saying. All right, that's what I do when I lecture. I just set it up, and I've been setting up from the first day on. I say, here's the format. Through this format, we will communicate. Everything in life is formatted, guys. Everything in life is formatted. You cannot communicate outside of any sort of format. All right, we speak English in the United States instead of something else. If somebody starts to speak a different language to you, you won't be able to communicate. We use the Arabic numerals as opposed to the Roman numerals. We have a great alphabet that we're using. In physics, in sciences, it's the same. We use formulas that everyone agreed on. And once again, the force diagrams. I mean, force diagram justifies a solution. Everything is going to come out of this. Most of you guys have half-assed force diagrams. I could have done it. I can still do it. It's not a big deal. But it's a college physics course, so I'm thinking, okay, it's not a big deal because it's more of a math literacy at this point, more than anything else. You won't be using it for the most part. Still, if it's not set up correctly, everything else that you do after this, if this is not set up right, I can just easily give you 1 point and say we're done. All right, so you have to just make sure that your force is set up correctly. When you set up the forces correctly, this data literally has to go here because these are similar or identical triangles in essence. Okay, once this is set up correctly, then you could do anything you want. So everything else is going to be justified based on this. All right, so this is a good exercise. So I'm doing my conversions, obviously. Before I forget, I want to say that the forces, the speed is going to be constant because it says speed is steady speed. And the rest of it is, I'm looking for power. All right, so my power equation is going to be located here. Okay, so power, in this case, what is it that I'm looking for? Because now I have to make a decision. Okay, so I'm going to pick an equation based upon what's given to me. All right, so notice that I got my speed. So the speed is given. So I say, okay, I know the speed, so it makes sense to use this equation. So power is going to be how fast this force is going to be transmitted. All right, so that's the one that we will get to use. All right, so the next question is, when you put this up, okay, notice the thing that I did. I'm going after power. I'm picking my equation, and I just explain why I end up picking this one. Because the only reason why I'm picking this one is, as opposed to anything else, is because the speed is given. And so it makes sense to use that one. Next question is, what is this force? Okay, now this is where it gets kind of complicated. And this is where you guys usually get really nailed on the test, because you're just gonna, if I give you a problem like that, I know you will follow exactly what I did, thinking that there's a secret recipe. I'll look at it and immediately I will understand what you're doing. In reality, that's not the way this works out. You have to justify it. You have to assume that the person who's grading has no idea what you're doing. All right, so which force do you use? Well, now you have to really dig into the meaning of this formula. What this means is this power comes from this force being transmitted at the speed. All right, so this is the drive force. This is the force that drives the car. So it cannot be the frictional force. It's definitely not the weight. It's not the normal force. So it's the drive force. It's what's generating the power at this point. So I go, okay, so this has to be the drive force. Okay, I would explain that if I'm solving a problem in writing, obviously. I'm just going blah, blah, blah. I'm just telling you what it is. So this force is the drive force that generates the power. Immediately, I go back, make FD, and all of a sudden, I interpret the formula for our purposes. Drive force is not given to you. That is not that easy. So where do you get drive force from? I mean, there's no drive force, but there's government information here that I can utilize. I know that this car is going up at a constant speed. I can come up with a drive force because it's also the motion along the x direction, right? So I can sum up the forces along the x direction. So that's what I'm going to do. Just sum up the forces along the x direction. Drive force is in the positive x direction. Frictional force is in the negative x direction. So that's going to be negative. And on top of that, here's the reason why this setup is really important. W, the weight, is also as a component along the x direction. It's got a component along the negative x direction. So the component of W is in this direction. It's the opposite over the hypotenuse. So this is hypotenuse, this is the opposite side. So opposite over the hypotenuse is going to be the sine of the angle of W, which is the sine of the angle of mg that we're looking at. So there's going to be a negative here. So it's going to be mg times the sine of that angle. Okay. There's no way you can come up with this equation if this is not set up correctly. All right. There's no way. In real life, it doesn't happen. So everything is connected to each other. Everything has to be just right. This is like the house of cards. If you're faking something, everything is going to come back down. Everything is just going to collapse. And most of your solutions are kind of like, it looks like physics, but it's like movie physics. The gibberish stuff that you see in the movies on the board, I look at it, oh, okay, I see what's going on. All right. And so the net force along the x direction is going to be responsible for the acceleration along the x direction. So what's the acceleration along the x direction? Well, along the x direction, the speed is along the x direction. All right, I should have specified that. Now I'm talking about it. All right, so obviously its speed is along that direction, but it's a constant speed, so which means that there's no acceleration. So speed is constant. The direction of motion, which is the x direction, so there's no acceleration here. So which means that not you can isolate B. I'm just going to move all the terms to the right, and then just substitute that back into that formula. And that's it. All right, so that's it. So we have an expression for F. We know the mass of the vehicle. We know what G is. We know the angle. We know the speed. It's going to be 60 miles per hour. So just plug the numbers in. Do your conversion. And the horsepower in this case is going to be 110 horsepower. So that's car, the exact same car that we were dealing with. All right, so for a car to be able to go up this steady speed of 60 miles per hour up this incline, it's going to be 110 horsepower. All right, so that was question number 14.